All right, we're going to convert polar equations to Cartesian or rectangular, and then we're going to go Cartesian to polar. And the key for this, guys, is those substitutions we learned earlier, which of course are x equals r cosine of theta, y equals r sine of theta. We also have x squared plus y squared equals r squared, and then more rarely used, but the tangent of theta equals y over x. The inverse tangent of theta equals y over x. The tangent of theta equals y over x. You could also do theta equals the inverse tangent of y over x, of course. So either way, you could use that. But we're going to use these over and over again to substitute and to manipulate these equations, similar to how we did with parametrics. And so first we have r equals the secant of theta. And so first thing you should hopefully notice is, wait a second, r equals 1 over the cosine of theta. And if you look at these, it should scream this right here. Wait, that is just this in disguise. So if we multiply by the cosine of theta, of course, we just get r cosine of theta equals 1. Well, what is r cosine of theta? That's equal to x. So this is just the function x equals 1. So the polar graph for r equals secant of theta would just be this line. All right? That is the polar graph of it. The radius is equal to 1 over the cosine of theta. And if you plugged in those values, you'd get that. And you can use your calculator if you want to plug some of these in polar mode just to practice and get the feel for it. Next, we have the Cartesian coordinate case for r equals 3. Well, hopefully, right away, if you hear r equals 3, you instantly think to yourself, well, that's just a circle with a radius of 3. And I'm going to let the Notability give me a circle there. And so I know what I'm going for here. So if r just equals 3, I don't really have a good substitution here. I don't have the cosine or the sine to deal with, where like I had a cosine here. But what I can do is I can just square both sides, and now I'm looking at this, and that makes sense because this is what the equation of a circle looks like. So I'm going to square both sides, so you get r squared equals 9. And then substitute in for r squared, x squared plus y squared equals 9. And what's interesting is, again, remember the formula for the equation of a circle is x minus h squared plus y minus k squared equals r squared. And if you look, it's just a shift to the left and to the right. Right? It's just a shift to the left and to the right of x squared plus y squared equals r squared, which is what we use for polar coordinates. And then the last one we're going to look at is r equals 2 sine of theta. And how do we manipulate this? Well, again, what you want to look at here is, man, this r isn't great for me. If I divide by r, I'd have 2 over. That's not good. And if I just had an r here, r sine of theta is y. So if I just had an r here, this would be 2y. And if I had another r here, wait a second, that'd be r squared. So let's do this. Let's just multiply both sides by r. So we multiply both sides by r. We get r squared equals 2r sine of theta. R squared is x squared plus y squared equals 2y. And you might say, oh, well, okay, I'm done. Well, but let's get this into this form that we showed right here. And so what will we do? We're actually going to complete the square. So we're going to have x squared plus y squared minus 2y equals 0. And why did I leave the space there? Well, because let's do this whole b over 2, right? So b over 2 quantity squared, okay? And so negative 2 squared is positive 1. So I'm going to add 1 to this side. I'm going to add 1 to this side to balance my equation. And that gives me x squared. And what that did is that made this right here a perfect square trinomial. And of course, it's going to be x squared plus y minus 1 squared equals 1. And of course, we know that this is a circle with center point 0, 1, and radius of 1. Okay. Now, look how much more complicated, at the surface level this equation is than just r equals 2 sine of theta. And so, polar coordinates for circles and these curves can be much simpler. Now, going Cartesian to polar, these are, kind of tricks of the trade again, but now we have our circle, And so we want to kind of take it, and if you look, kind of what we just did, we want to kind of go backwards and figure out what this is as a polar coordinate. Now, something I wanted you to notice is here the y was shifted, and it's 2 sine of theta. Here the x is shifted, and so you might consider it's going to be some coefficient times the cosine of theta. But let's go ahead and let's look at how to solve this. And so we're going to have, x squared minus 6x plus 9 plus y squared equals 9. All right. And then if we change that, we have this x squared plus y squared. We really like that. This 6x is just 6 times r cosine theta. And then these 9s are going to cancel, actually. So we have x squared plus y squared minus 6x equals 0. Now remember, if we're going for a polar equation, we want it in the form of r of theta. So we want r to be alone, and we want theta to be on the other side. All right? So x squared plus y squared is just r squared. And then minus 6x is minus 6 times r sine of theta. And so now we can just go r squared equals 6r sine of theta. Divide by r on both sides. You just get r equals 6 sine of theta. You also, in this case right here, you could have factored out, right, an r. You could have said r times, on the step before that. Step before that here, you could have just factored out an r, said r times r minus 6 sine of theta equals 0. And then, r equals 0, that's not what we're looking for, but 6 sine of r minus 6 sine of theta equals 0, that would give you a valid solution. So that was another possibility there, but I'm just going to put this off to the side for now. And so this is the answer that we're going to go ahead and accept. So r equals 6 sine of theta. Again, it's a function. It's r as a function of theta. It's r as a function of theta. And so here on this one, we have xy equals x plus y. And so what are we going to do to solve this one? Well, let's go ahead and let's do x is r cosine of theta. Y is r sine of theta equals r cosine of theta plus r sine of theta. Which you might notice you got r's on, well, both sides. Okay? And so here you have r squared cosine of theta, sine of theta. And here, if you factor out your r, you have cosine of theta plus sine of theta. Divide both sides by r, then you just get r times the cosine of theta, sine of theta, equals the cosine of theta plus the sine of theta. And then now we're just going to divide both sides by the cosine of theta times the sine of theta. And you just get r equals the cosine of theta plus the sine of theta, all divided by the cosine of theta times the sine of theta. And you can determine bounds on these to make one full function, from 0 to 2 pi, for example. But we're just not going to worry about that for right now because, honestly, we don't have a ton of time to explore these this year. And then we're going to go ahead and skip the last one for now. You can go ahead and do it. And actually the answers, if you look at these, and I don't want you to look ahead, but the answers are actually just below here for you in your packet. They should be. And if not, let me just go ahead and give you the answer to that last one so that if you work it out, you can feel confident that you got it. So if you go ahead and you solve this one using those same substitutions we've been doing, you'll get r equals 2 square root sine of 2 theta. And to get that sine of 2 theta, you're going to have the substitution of 2 sine theta cosine theta equals sine of 2 theta. And that would be something that would be on your book, on your trig functions page. But again, don't worry too much about this last one.